To go. So I'm a PhD student between Mandriva in Paris and the Computer Science Lab in Tours. And I've been working for around 1 year now on the topic of verification in the kernel with model checking. So as part of this, I made a small survey of faults in patch kernel that I will present to you right now. It might not, I think 45 minutes is a bit large, but anyway, it will give you plenty of time to think for questions and to ask me at the end. So the presentation will follow this schedule. First, I'll introduce you the subject. I'll present you Undertaker, which we use to expose faults in the kernel. I will then present the methodology of the study, its results, and we will conclude on what work we should go on next time. So, what's our goal? We are interested in verifying the kernel, as I said previously. And it's obvious that vanilla kernel is not the one used by distribution by default. It's nothing new for you guys, but it's better to remember it. So, we ask ourselves one question: does it have the same properties? By properties, I mean we can find in the literature a lot of quite interesting number of studies of faults in the vanilla kernel, but we were interested to know if those studies were applicable in our case, and in fact in the case of any distribution. So to rephrase it, does the fact that we have page kernel change anything in the results of the literature? Previous survey has been done. The first one I found about was Chu et al. In Q1, and it was an empirical survey using the tools designed by Stanford people, which founded later the Coverity company. They extended GCC with some metal, what they call metal language, which they use to check for properties on code, and they applied it to the Linux kernel. This study showed that the main hotspot of failure in the kernel is in the driver's subdirectory. So they highlighted the point that we need to work on driver quality to remove all these faults. The kind of faults they were looking for was, for example, null pointer derecurrence, comparison between pointer and zero value, things like that. 10 years later, there has been an updated survey which was following the same methodology. It has been contributed by Nicolas Palix, as far as I remember, student or more students in some French lab. I think it's the LIP6. And one major point of this survey is that it shows driver is still a hotspot, but it's less a hotspot than previously. And there is a growing hotspot right now, it's the arch subdirectory. So right now, after this study, they concluded that the work that has been made on the drivers has had effects, enough effects so that now it should be targeted against the arch subdirectory. So we use Undertaker, so I'll explain you a bit what it is. Maybe some of you already know about it. Undertaker goal is to find configuration defects. It's pretty simple to understand. You have the kconfig on one side, which defines all the configuration flags that are available. And on the other side, you have a bunch of if-def in the source code that uses the same configuration options. And their goal is to check consistency between what's available and what's used in the source code. So they presented what they call the live framework in a couple of papers. And two main ideas, two main points in the tool is the variability model produced by Coccinelle and the variability implementation which is in the source code. They extract both, they transform it to Boolean formulas, and then they use a simple stat solving, for instance picostat, to check for inconsistency. It allows them to find dead code or undead code, either dead code or undead code on one architecture or on all architectures. So it can be very useful, and maybe it might seem not that useful right now, but they gave an example which is a CPU plug feature. If you follow the mailing list, I think you have already heard about it, but for those who did not, like me, CPU plug has been broken for 6 months, a couple of years ago, because of configuration inconsistency. So in fact, there was missing if-def to enable the plug feature, and it took 6 months before being fixed. This is the kind of issues that are triggered by this tool. The report having identified 19 issues as stated in the paper, and 14 were already fixed or in instance to be fixed for an old kernel right now, but it was a pretty interesting result. I have been unable to run the Undertaker 1.1 on kernel that is older than 2630. They also are already aware of this, but it explains why I have been limited to a bit recent kernel in my study after. So now I present you the methodology that I have been following. First of all, you might ask why did I choose to use Undertaker? It's not the only one tool that can find defects in the source code. You have, as I said, Coverity, which is not free software. You have an implementation which is free software under the name of Smash. You have also Coccinelle, which is pretty well known, I think, since it has checks included upstream. But at the time I started this study, it wasn't available in New York. Now it is available in the Cooper version, so it will be in the next stable release. And I found Undertaker to be much more easy to use and understand from feedback point of view, because it tells you whether there is dead code or not dead code in which file, so it's pretty easy to treat. It's pretty fast to run, so it is testing. On a small virtual machine with 2 GHz CPU and 1 GB of memory, it took me about 20 to 30 minutes to analyze it. So when you have to go through tens or dozens of kernel, it's better to be fast. There has been already huge work published around Coccinelle too, by authors of Coccinelle. And since Undertaker is much more recent, there is less work being published on this. But limiting ourselves to configurability is not a final point, it's just a preliminary step to see the field, to polish tools, to to have some feedback from the community too. Okay, so now we want to follow the number of faults in our kernel and compare it to the upstream or non-patched. So as in previous paper, we will follow the subdirectory count because it is easy to understand, it allows to focus easily where are the hotspots, and since it has been done like that in the literature, it's better and easier to compare ourselves. We had, however, an issue because we are interested in paged versus non-paged kernel, and it's not the same code base. So only accounting the number of faults will not be efficient nor have a real meaning because possible influence of the patch, it's no surprise for you, it can change add or remove lines of code. And if you count only the number of faults, it has no meaning. So we introduced a simple but I think meaningful enough measure. It's simply the number of faults in a directory divided by the number of lines of code in this directory. So it gives us some quality measurement over the code. Then we can use to compare between a patch and non-patch kernel without having to deal with the meaning of the patches itself. And then we have the comparison point. So we took a simple approach, just doing the difference between one channel and the other. We might discuss, it's open to discussion, the way we measure it. It's just an idea. Maybe there is a better idea I did not thought of, but this way we have an easy to use metric. Positive difference means that there is an improvement between in a kernel y over x, and vice versa. If it's negative, it's worse. So it gives pretty easy to understand and interpret results. However, I'm open to any suggestion on this point because I don't have necessarily the experience or maturity to have a better point of view. So now I present you some results. First, before going to the results, I wanted to make sure that my results were comparable to what I've already been done. So I run Undertaker on the same kernel already used by Nicolas Palix in the publication number 2. There will be reference at the end of the slide. And I took a point of comparison on the driver subdirectory and arch subdirectory, since they are the more meaningful and the one where the faults are concentrated. And I computed some kind of ratio between the number of faults of each one. And for Coccinelle analysis, it gives a figure, 0.75. And doing the same computation with Undertaker results, we got the same ratio. So it's not extended study, but it shows that at least we can compare the results between what has been done by people of Coccinelle project and results given by Undertaker. So now, the first chart, nice. I don't know if it's easy readable. On the bottom you have a different kernel version. Those are the upstream version from 2632 to 2638. And on the left axis, you have the frequency per 1,000 of line of code. So you can see that frequency is pretty low. In fact, we have less than one fault found by Undertaker for 1,000 line of code. And we found the same results on Coccinelle. On the Arch subdirectory, which is the green top line, and on the driver subdirectory, which is the cyan second top line with these small boxes. So this is where I computed the ratio I talked about. And you can see that, how to say, number of faults is approximately decreasing. And the more important part is that Arch subdirectory shows more fault than the driver subdirectory. So we get the same result than previous study with other meaning of measure. This is interesting. Now, we can say that new kernel is not always the best kernel. This has been run on Debian 2.6.37 release, 2 different releases. So it's the difference I explained just before. I took figures from 2.6.37.1 and 2.6.37.2, just made the diff between both and charted them. So we can see that there is an improvement on the documentation subdirectory. I just have no idea why it comes up. There is a slight improvement in the Arch subdirectory, which is the first yellow, green boxes, and there is a drop on the kernel subdirectory. A huge drop. You see just as a picture. But in fact, if you look at the scale on the left, you can see another interesting thing. It's that the difference is very, very, very low. We are at 0.008 of fault frequency per 1,000 of lines of code. So there is a difference, but it's not very meaningful. This is between just 2 releases of the Debian kernel. Now, I wanted to compare vanilla and latest Debian release over the same version. And now it's more interesting because you can see an improvement global. There is some downsides, but globally figures are positive. So if we get back to the definition of the difference, then it means there is an improvement. Again, this improvement is pretty small, in fact. If you take a look at the scale, we are on the same level, but there is an improvement. We made the same kind of measures over the Mongrel 2.6.33.7 kernel, just to check if we were having the same kind of results. And it turns out we have the same kind of results. We have an improvement over the driver subdirectory. And once again, you can see that the scale shows that this improvement is very slight. In fact, it's even slighter than the Debian one, if you take a look. We were around 0.004 for the Debian improvements over the drivers of the research, and now it's just half of it. So there is improvement, but it's very, very, very light. There is a small, there is a regression, or you can say this, for the FS subdirectory. but once again, it's to be recite. This one is pretty hard to read, but it's open source kernel from 2.6.30 to 2.6.37. And the interesting part here is to compare with the first chart I showed to you, which was this one. So this one is just over 2.6.32 to 2.6.33, and it just major releases, while for open source there are all sub-releases. But if you take a look to the general form, in fact you see that it has exactly the same behavior. So the fact that open source, this is not the vanilla open source, the vanilla kernel work by open source. This is the patch open source kernel. So once again, we get the same figure between vanilla and patch kernel. There are some slight drops, but we can get one slight tendency, which will be a kind of a conclusion. There are very few differences, and when there are, in general, they are in favor of patch kernel. Another interesting thing is that we can show the number of faults is decreasing, either when measuring one tool, Coccinelle, or when using another tool, which is Undertaker. So it means that the kernel code quality is improving over time, whatever the point of view of analysis we have, since Coccinelle and Undertaker doesn't share the same point of view. So this has been some preliminary work. We need some more powerful and polished chain tools for this kind of study. I think we need to introduce some other methods to the project. So for now, I only use Undertaker, but we could use also outputs from Coccinelle, and maybe Smash or other tool might still help. I think it would be good, because I have found nothing about this, to have an history of those kind of faults, just to have charts like I showed you, to see where we are heading, see if the quality is improving, things like that. And I think this should be targeted to easy use by any distribution, so that each one can produce its own results and see where its kernel is headed. I think one of the important code is to investigate more precisely to qualify the difference, because there are differences. For example, on the subdirectory drivers, number of differences found by Undertaker is something like 20 to 30, so it would be interesting to have a look to what are the differences. Maybe there are things very important. And I think it's all. Now, the references. If you have any question, I'm glad to answer. Yes.
What's the name output look like?
Sorry?
So you run the tool and you see something. What do you see?
You just see the.
Give an example.
I don't have an example right now, but the output is pretty simple. It just gives you the path of the file involved, and each block of the source code that is involved in a fault, in a configuration defect. So the source code is divided in blocks, which are roughly the EDF defined. And it tells you here you have some block that is not activated, or here you have some block that is always activated, while it should maybe not. But for now, I just took this output and I limited myself to the first part of the path to get the subdirectory, and just I computed some sub. So it's pretty pretty naive, but I think can go much more.
Are these tools freely available, or are they?
Yes, Undertaker is developed by some guy I met at the Fosdam in February, and it's part of the Vamos project brought by the University of Erlangen in Germany, and it's free available. It's packaged in Debian, as far as I remember. I packaged it in Manjula. I think it's also available in Fedora. And it doesn't need a PhD to be run.
These tools are static analysis tools, right?
Yes.
So what, do you have any idea of what the false positive rate is on these failures?
Yes, they gave some figures, but I don't have it in mind. You can check the paper, especially reference number 3 and 4, which is done by people from the Undertaker project. They also have some kind of bugs for now. You see it when you run the tool. It says it can pass something, so it might. It means the results are maybe not totally complete. Okay. But I don't have the figure of false positive right now.
My previous work with tools like Coverity is that you have to babysit the output and train it for your project, because very often it's just
Yeah.
wrong.
Yeah. But they are targeting a pretty small subset of complex programs, so I think false positives are not that big, as far as I remember.
So the fault you're trying to detect is dead piece of code?
Sorry?
The fault that it tries to detect is dead piece of code, like code that will never get executed?
Dead or undead.
Like for example, if you found it's 0 and a piece of code, and it will say that the piece of code will never get executed?
Yeah, but it might also be the reverse when you have code that is between if-def and that the if-def have been removed by another patch, so that the code get executed every time where it shouldn't. Was I clear?
So like if you have to embed it, like found if, like it could detect a thing that one will never get executed?
Yeah, I think so. Yes?
Yes, I was thinking about the way that you calculate your metric
Yes.
to see if there is an improvement or if it's getting worse.
This one?
Yes, well, maybe the one before that where you count the number of faults divided by the numbers of lines in the source code.
Yeah.
If the patch only increases the lines of source code without introducing any faults, you're going to see a decrease in your, of faults with your ratio, but it's not really an improvement per se. It's just that you have more lines of source code.
Yeah. I have currently no idea how we could deal with it.
Okay, was there any reason you still use that instead of the raw number of faults?
No. It's just I thought of it, I run it a couple of times, and I saw it gave interesting results, but I'm open to any suggestion.
Yeah,
If you have any idea how it could be improved, I'm open.
Yeah, I'm just thinking that any change in the number of lines of source is going to affect your result.
Yes.
And it's not necessarily what they're looking for.
Yes. But I have currently no idea how we could.
Well, maybe just the number of faults as a raw number, but I understand if you want to have some kind of ratio so that it's easier to compare.
Yeah, because in fact, first when we did this, and it gave biased results, because if we have a big patch that has a lot of scope, okay, it might introduce very, very high number of faults, and the fault rate will increase, it's normal. But should it increase such? It should take into account that the fact that there is a lot of code in it. This is the part of this was the main idea.
Yeah, I can see.
Maybe we should check with the patches that correspond to the code and check if only for the Undertaker case, check if the added code concerns some configuration point. This way we could see if the added code has an impact over what's measured by Undertaker or not. Maybe it would be a better way to measure it.
I don't have a clear solution for you, I just wanted to point that out.
Yeah. Yes?
Are there other tools that does deeper analysis of the source code that they could run on the kernel?
So you have also Coccinelle, as I stated, which Coccinelle was designed to enforce API evolution, and they also decided to use it for bug finding. So there are a couple of rules that are available in the Cocci-check subdirectory, in the script subdirectory. And it allows to find errors such as pointer dereferences when it's not a good thing, things like that. You have Smash, which is a re-implementation of coverity, mainly, because coverity was not free software. You have Sparks, which is more, it's not that deep. And as far as I remember, you also have some kind of lint, but I'm not sure it's used for the camera.
Thank you.
Any other question? Yes?
Out of the 15 courses you committed to the mainline term that were accepted, are they documented in your paper?
It's not me, it's an Undertaker papers. I don't remember if they documented it. I think you can search the Kernel to see people from Undertaker project in patches. I can raise them if you want to see what has been fixed. Just send me an email. You have my mail here. Yes?
How do you deal with configuration of the kernel? Did you use one config for all the tests? Or
Yes, I use the same config for this text. In fact, I use the default config. But the way Undertaker works, it doesn't rely on the config enabled, but on the configuration option available.
So it does all the permutations?
Yeah, and it also does checks for every architecture. So you have this difference between dead code, undead code, and globally dead or globally undead. Dead code is just dead code that is dead in one architecture, not architecture. Undead is the same, and when it's globally dead, it's dead everywhere. Are we finished? Thank you.